All right, motion along a line. This corresponds to the Khan Academy under differential calculus, derivative applications number 2. All right, so motion along a line. The position, velocity, and acceleration of any particle have a beautiful relationship. We're going to talk about that. Recall the derivative just means slope. So when we're talking about the derivative as a slope, it's also just the rate of a function at a given point. It's the rate of change of a function. So it's really the velocity, because velocity is really the rate of change of position, right? So if you had some function, let's call it s of t, it's usually what we use for the name of position function, we could find its velocity by taking the derivative of this function, and that would actually represent a function for its velocity at any point in time, according to time t. And in the same way, its acceleration would be a derivative of velocity. And so they have this beautiful relationship that if you have a position function, the derivative would be the velocity, and the derivative of velocity would be the acceleration. And we have some basic rules for how these things relate to each other. Just something you kind of have to memorize here eventually, but some basic rules for velocity and acceleration. If the velocity and acceleration signs are the same, then the particle is increasing in speed, I should say, increasing in speed. So notice here I have velocity is positive, velocity is negative, acceleration is positive, negative, negative, and positive. So notice when they're both positive, it's increasing in speed. But when one's positive and one's negative, then we could say it's slowing down. Or if the velocity is negative and, if the velocity is negative and the acceleration is positive, then it's also slowing down. If they're the same sign, though, both negative, then it's actually speeding up. Even though they're both negative, it's just because it's moving in a negative direction. But it's doing it in a increasing manner because it's going in the same direction. The negative and the positive really just have to do with direction. So moving to the right is a positive velocity, moving to the left is a negative velocity. The more we play with this, the more I think you guys will understand it. So here's the first problem. It says the position of a particle moving along a number line is given by this function s of t 2/3 t cubed minus 6t squared plus 10t, where t is the time in seconds. Okay, and so obviously we're starting it after 0. The particle moves both left and right in the first 6 seconds. What is the total distance traveled by the particle? Okay, real quick, what does this mean? Well, let's just think about it. Let's say I started here and I moved this way 2 units. And I move this way, let's say 5 units. Okay, that would be positive direction of 2 and a negative direction of 5. But how far did I go total? Well, I went 2 plus 5. I went 7 units total. Even though I ended up 3 units away, I still did a total of 7 units. This is kind of like the idea of like if you walk to the store and back, and you walk a mile to the store and then you walk a mile back, you wouldn't say, oh, you walked 0 miles because you're at the same point. You'd say you walked 2 miles total because it's distance there and back. So we're going to try and figure that out. Well, the only way we can really figure out the total distance is if we could figure out, hey, where did we turn around? Where did we change direction? And then we could add up the distance here and the distance here, and we could say, oh, we know the total distance. Well, in calculus, what do you think represents that point in time when we change direction? Okay, think of it as a graph. I went up so many, down so many, up so many. If you think of it this way, I'm changing direction right here and right here. I'm changing direction when my slope is 0, right? So I could say, okay, how far did I go here? How far did I go here? And how far did I go here? That's what we're really looking at. So we really need to know when the velocity is equal to 0. So they give us a position function, and we know that the velocity function is simply the derivative of the position function. So I'm going to go ahead and find the velocity function here. So velocity has to be, well, if I bring the 3 down, that's going to cancel out nicely to be 2t squared, then minus 12t, and then plus 10. So now I have the velocity function. Well, if I want to know when basically when the direction changes, it's going to happen when the velocity is 0, so I'm going to go ahead and set this thing equal to 0 and solve. Right away I see I could take a 2 out of everything, so I'd get t squared minus 6t plus 5 equals 0. Then I could factor this nicely, and I get a t minus 1 and a t minus 5 equals 0. Okay, so that means my solutions for when the velocity is 0 is when t equals 1 and when t equals 5. All right, well, I'm going to use the same thing that we've been doing before. I'm going to make a little chart. And I know I have some key points here, or some critical numbers. I know 0 and 6 are critical numbers, and now I know that 1 and 5 are critical numbers as well. Well, I'm going to make a table just like we've been doing. So here's all my t values. I'm starting at 0. I know that 1 is important, I know that 5 is important, and I know I only go to 6. And get some basic ideas here. I got my s of t values and my v of t values. And I also care what's happening in between these values. So this is t in between 0 and 1, this is t in between 1 and 5, and this is t in between 5 and 6. So some values you could just kind of plug in for there. I mean, you could plug in a half, maybe a 3, and maybe a 5.5. And now we know the velocity when t is 1 is 0, and the velocity when t is 5 is 0. And so what we really want to know is, what is the velocity in between? Is it positive or negative? Because if it changes velocity, then it's changing direction. So we can evaluate that by plugging into the velocity function real quick. So if I plug in a 0, I'd get a positive 10. So we know that's a positive. If I plug in a half, I'd get another positive value. You could do this on your own if you want to check it. If I plugged in a 3, I'd get a negative value. If I plugged in a 5.5, I'd actually end up with another positive value. And if I plugged in a 6, I'd end up with a positive value. So when does this thing change direction? Well, right here and right here. So that means I just need to know the position when it first starts, when it changes direction from positive to negative here, when it changes direction from negative to positive here, and then when it ends. So I just have to evaluate these 4 points. So I can do that by just plugging in these values into my position function and figure out where the points are, what the position it has at those point in times. So you can work this out on your own, or you can use a calculator to calculate this out. All I'm doing is plugging in these 4 values, these 4 blue values here, into this function. I've already done it, did it ahead of time, and I got 0, of course, because that's our starting position. Then at 1 second, I had a 4 2/3. At 5 seconds, I was at negative 16 2/3. And at 6 seconds, I was at negative 12. Okay. Now remember, I want the total distance. What is the total distance traveled by the particle? Well, this is like saying I went 4 2/3 to the right. Then from that point, from 4 2/3 to the right, I went to negative 16 2/3 to the left. So I need to know the total distance covered there. And then from negative 16 2/3, I went to negative 12 to the left. So I need the distance in between each of these numbers, and I'm going to add those all up. That's how we're going to get our answer. So let's think about that. From here to here, how far did I go? From here to here, how far did I go? And from here to here, how far did I go? And I just want the absolute value because I want the total distance. Well, the first one's easy. That's just 4 2/3. The next one is 4 2/3 plus negative 16 2/3. So that's 21 1/3. And then to go from negative 16 2/3 to negative 12, that's another 4 2/3. Add these 3 distances up, and you get 30 2/3 units. So the total distance I traveled is 30 2/3 units. Alright, suppose a particle's position can be represented by the function s of t equals 2/3 t cubed minus 6t squared plus 10t. For what interval of t is the particle speeding up? Okay, remember we said speeding up, that's when the velocity and the acceleration have the same sign, okay? So I'm just going to make a little note of that. When I'm talking about speeding up, that's when the velocity and acceleration have the same sign. I know it's messy, but just a quick note of that. Okay, this is the same function we used before. So we already did the velocity function for that, so let's just do that again real quick. So we know that the v of t equals 2t squared minus 12t plus 10. And we already set this equal to 0, and when we did, we found that t equals 1 and 5. Those were our critical numbers. Well, now I want us to also find the acceleration. And remember, the acceleration is simply the derivative of velocity. So if we take the derivative again, we would get 4t minus 12. All right, well now when I set this thing equal to 0, I would get 4t equals 12, and therefore divided by 4 divided by 4, I get t equals 3 is another critical point. So I have 3 critical points here. They didn't give me a domain here other than we're obviously looking at points in time when t is greater than 0. So now when I make my chart, it's going to be a little bit more specific. So let's go down here. I'm going to kind of leave those values there and make this chart. So here's all my t values. And I know I'm starting at 1. And the next critical number I have is 1, and then 3, and then 5. And then I didn't get any other critical values, so I guess I'm going to go up to positive infinity. And then I want all the values in between, or I'm going to look at it in between all these critical numbers. And make my chart accordingly. Okay. And I really just care, since I just want to know the intervals and where it's speeding up. That's all they're asking for. I just really care about velocity and acceleration. So I'm really going to look at just these two. I could put the s of t function in there, but it doesn't really matter for what we're doing. And you can use what you did from the last question, because it's the same equation as the last question, to kind of fill in this chart. If you want to do it all over again, you can. But we already did it, so I'm going to go ahead and just fill in these values. We knew that this is positive, positive, 0. And then from 1 to 5 it was negative, and then 0 at 5, and then positive again. We already did that from the last question. Okay, that's the same values. But now for the acceleration, we could just plug in these values to here. So what does it equal at 0? Well, 0 would be negative. Anything less than 3 actually would give us negative. So I'm just going to say negative, negative, negative. Here's when I get a 0. Then anything after 3 is going to give me a positive. That's a weird plus sign. There we go. All right. So remember, all we need to know now is the intervals when it's speeding up. And remember, the intervals when it's speeding up is when they have the same sign, when velocity and acceleration have the same sign, or when the first and second derivative have the same sign. Well, we can see that. We could see that happens right here. And we could see that happens right here. And so when is the intervals where it's speeding up? Well, it is speeding up when t is, or from when t is 1 to when t is 3, and from when t is 5 till infinity. So those are the two intervals when it's speeding up, because those are the two intervals where it has the same sign. So there you go. See you guys on the next video.